Previously we discussed a lot of the pressure gradient and such. Now we discuss the rest of it. So derive the shear stress of the flow. Okay, so shear stress of the fluid flow. So how do you do it? If you remember, the shear stress is calculated by this is the one. Okay, so you're gonna come back here again. Okay, this is the shear stress formula. There is two type. One type is the is this one. Okay, this is shear force over area. While the other thing, while the other expression to represent shear stress is actually this one, the viscosity multiplied by the change in the velocity across um, the it's just shear strain rate lah. Okay, somewhat. So it's not about across y or what. It's just yeah. So if you were to come back here, okay. So this is the same thing that I've explained. T, I mean tau actually is tau goes to nu, and then this is actually radius and x direction. So we are actually going in the x direction, well, with a certain radius. Okay. So this nu is the viscosity, while this is the change in the velocity. So if you remember, our velocity is actually this dude over here, which is the one that we derived very earlier in the very early part. This one, okay. So if you were to sub in over here, you have to differentiate one time because of this formula. So if you differentiate in terms of radius, you will get this thing over here, right? And therefore this is, and therefore when you sub it in into your equation, you will get your values over here. So this 2 divided by 4 will have half r partial p partial x. Okay, and then this nu and the nu over here will cancel, so therefore you have this thing over here, and this is your shear stress. Okay, and your shear stress is also dependent on the pressure gradient. Okay, so this is we clear away the shear stress already. Is quite straightforward. Okay, so I hope you understand the shear stress part. Okay, so let's continue. And then where and what will be the maximum velocity of the fluid? Okay, so is this gonna ask where will be the maximum fluid? Okay, and calculate it. Okay, so where maximum velocity occur, so it's actually the center of part where r is equals to 0. So where the hell is it? So it's actually at this point. As you can see, it's way faster than this two over here. So this dude is actually the fastest. So this is the maximum velocity it is. The reason why is because at first when you flush in, it should be all the same speed. However, due to this boundary condition, okay, this part, there's a frictional thing that actually pulls back all this thing. So therefore they're slower than the one that is, the initial, so this is the maximum velocity. Okay. And then the rate of change of this is equals to 0. So what does it mean? This means that you're going to calculate what is the maximum velocity. So what is the maximum? So we know where, so we need to calculate what. So in order to calculate what, you know that this is actually small r, right? If you remember our previous video, we talked about it. Okay, talk about this is maybe I zoom in a while. So this is actually the distance r. Okay, r can be equals to 3, can be equals to 2. So for example, if r is at this side, r equals to 2. So if r is equals to 3, and if it's all the way up to here, so r will be equals to r. So r is simply a notation to show that there's a distance or something like that. It's a radius lah. Okay, so the radius that you're looking at. So for this case, this is as you know that this is the maximum velocity. So therefore r is equals to 0, right? At this point. So we know this condition, we can actually sub it into our velocity equation, which is this one over here. So in other words, it's also this one over here. This is the one that you found out very early in the last week. Okay, so let's continue. If you sub in r is equals to 0, and then and then partial r is equals to 0, because r is equals to 0, you differentiate the velocity across r, there will be 0 because it will not be changing anymore, right? At this point, u will not change, right? Since r itself didn't change at all already because it's always at equals to 0. So you always, there will be no changes at all. Okay, there will be no changes at all. Okay, you may wonder, if r equals to 0, then isn't it equal to infinity? No, okay, this is simply saying that changes in r, if there is no changes in r, definitely there's nothing changed. That's all it says. Okay. Although contradictory, it actually becomes infinity, like this is 0. But then the definition isn't that. Okay, so this is, so don't digest this. Just digest that if r changes, okay, there will be a certain changes in velocity. If r doesn't change at all, then there will be no changes in velocity. Like that's a simple explanation. Okay, and therefore, if you were to still go back, okay, so you know these two conditions. What can we do is actually to sub in into our equation. Okay, so from here, okay, hold on. So I decided to paste the equation from here. Okay, this is the velocity equation. Okay, I just paste it here and then I contrast it so that you can actually see it clearer. So you know that our shit. Okay, so hold on. I'll invert color. I invert this. Okay. So you know that r will be equals to 0. Okay. So therefore, hold on. So therefore, this will become 0. So 0 minus r square will be r square over 4 nu partial p partial x. So this is simply the maximum velocity. Okay, so we have calculated the maximum velocity. That's all. Okay, so let us go to this one. What will be the average velocity of the fluid? Okay, so just now it's maximum, now it's average. So how we're gonna calculate all this? Average velocity, as you know, if you remember, is actually this one, right? When fully developed is this. However, if you can take all this throughout and then you take a mean average of them, it can actually become this line over here. So you take this piece, you take this piece, you take this piece, and you sum it up together. Okay, and then you divide by how the length of this, you'll get average. So how do you get this average? How do you know that you cannot unless you're gonna integrate them. Okay. So how you gonna integrate? Apparently this is not integration, okay, because it's like you're talking about cylinder. Okay, if it's cylinder, you want to integrate, you're going to integrate the whole radius. Okay, this is cylinder. If you want to integrate, you're going to integrate the whole radius from r to 0, and then I don't know how the hell. I'm a bit tired. But what the approach is, right? So if you can actually try to integrate, you can actually oneself do and do. But I recommend, not recommend, but I will want you to actually use this approach. Okay, so this approach is that is the velocity is actually you let it fill up the pail and also measure the time. Okay, so what does this mean? So imagine you have a pail, okay, over here. Then you know your maximum velocity, you know your velocity is gonna, you know your flow rate, okay. Okay, so this equation uses the flow rate equation. So the value is actually minus pi r4 over, so this is the flow rate. If you remember back our very early part, this is our flow rate, pi r4, if we were to compare. So let me show you comparison so that you can trust me. So guys, zoom. So this is pi r4 minus 8 nu. So this is the same thing. I didn't cheat you. So this is the flow rate. So the amount of flow, okay, so let's say you have a tap over here, and then the amount of water flowing in, okay, the amount of flow rate, you know that flow rate is across time, right? So it's meter cube per second, right? So you time how many seconds you take, and then you know your volume, okay, you divide it by the area of this pail, and then you can get your meter per second. So this is the average. Because your flow rate is this amount, correct? And then you divide it by whatever circular pail that you're gonna use, right? So you can get the average velocity because it doesn't have any, it's just a number due, something like that. So in other words, is the average velocity in this sense is saying that filling, so how much height can you fill up per second, something like that. Okay, so how much height of the pail can you fill up per second. So this is just an example analogy, but this analogy can be applied to actually calculate the average velocity. So this is actually a pretty good analogy. It's not by me, but by my lecturer, so it's pretty cool. Yeah. So let's continue. And then if you were to do that, so let's continue first over here. So this is your flow rate. I already proved to you that I show you that this is the flow rate. And then divided by area, you know that it's circular pail. Circular pail means a pi r square. So we have this over here. And what you're gonna do is actually cancel out this r square and this r4. You have r square over here. Okay, so maybe I should do it in terms of so once I cancel this, I'll have 2 over here, right? And then what can I cancel? I can cancel the pi also. So this left me with minus r square. Okay, 8 nu. So this portion over here is this one. Well, this one becomes 1 already now. Okay, and then this is partial p partial x. So you have the average or mean velocity meter per second. So this is your average velocity. So I've cleared away up till here. So next video I'll talk about Reynolds number and entrance length. After which I will go through the extended version of this one, and then we'll go into Bernoulli's equation. So I will see you in the next video for other stuff. See you.